To gain the freedom to deploy code independently, modern software engineering divided the traditional single code-based monolith. We broke our applications into hundreds of specialized microservices. We traded rigid infrastructure for agility, but in the process, we created a complex web of network dependencies. Running those decentralized nodes requires a runtime dependency tax. Instead of functions communicating instantly within a single environment, they now send messages across unpredictable networks, requiring immense engineering overhead just to ensure those messages are received. This architectural map shows how a standard digital action navigates that web. When a user clicks Checkout, their request enters a payment microservice. The card is charged, and the gateway prepares to pass that data downstream to update the inventory. But before the inventory service can record the order, a sudden network timeout occurs. The connection severs in the blind spot between services. The result is a ghost transaction. The user's money has been deducted, but because the inventory service never received the data packet, the corresponding order does not exist in the system. This architectural failure has a quantifiable business impact. It contributes to the 70.22% average checkout abandonment rate and the 32% drop in customer loyalty after a single technical glitch. For many retailers, these missing orders push them toward the 1% Stripe chargeback penalty threshold, which can jeopardize their ability to process payments entirely. Teams traditionally attempt to patch these network gaps using event choreography, placing message brokers like Kafka or RabbitMQ between services to hold data until the next node is ready. This logic flow illustrates a common breaking point, the dual write anomaly. A service successfully records a change in its local database, but the parallel attempt to update the external queue fails. The system is left in a split state, where one service believes the task is done, while the rest of the network is never notified. To compensate, developers write an explosion of boilerplate code. They build custom state machines, cron jobs to sweep stuck tasks, and complex retry logic, just to handle these inherent communication flaws. Software engineers effectively become maintenance workers for their own architecture, spending their time writing defensive code to mitigate failure rather than building business features. Temporal addresses this problem through durable execution, a model that abstracts the complexity of state management and failure recovery away from the application code and into the platform itself. In the temporal architecture, the front-end service acts as the entry point. It receives incoming requests from the client and routes them to the appropriate internal services. Those requests move to the history service. This is the core of the engine. It maintains an immutable ledger of every event and state transition in a workflow run. It tracks exactly what has happened, step by step. When the next step of a workflow is ready, the matching service acts as a task manager, routing that specific action to an available worker node to execute the code. If a worker node crashes mid-execution due to a server failure, temporal references the history services ledger. It instantly reconstructs the state on a new worker and resumes from the exact millisecond before the crash occurred. Because this architectural triad ensures that every state transition is durably recorded and automatically recovered, a transaction cannot simply disappear between services. It eliminates the need for developers to build manual safety nets for every network hop. For the developer, this platform is accessed through standard tools, such as the Temporal Python SDK. This side-by-side comparison shows the shift in effort. On the left, a developer must write nested try-catch blocks and retry plumbing to handle network errors. On the right, using Temporal, they write clean, synchronous code. They focus on the logic of the workflow, while the engine manages retries and timeouts in the background. Because state is durably persisted to the database, a temporal workflow can literally sleep for months. It consumes no compute resources while waiting and will not time out, even if the servers running the code are restarted multiple times. This long-running capability makes the platform a resilient foundation for next-gen agentic AI and systems that require human interaction. If an AI agent encounters a blocker that requires human intervention, the workflow can enter a state of suspension. It halts its execution, but maintains its full context indefinitely. The moment a human operator provides approval on their dashboard, the workflow resumes and picks up precisely where it left off. By moving the responsibility for reliability to the platform level, Temporal allows teams to stop building infrastructure safety nets and focus on the logic that actually drives their technology forward.